After I worked out how to make any magic square and wrote it all into a book, I considered this quest completed. I figured it all out and I even wrote a book about it. There was nothing more to do. I barely thought about magic squares for a couple of years actually. And then I took a programming course. One of the first assignments we got, even before we got to the actual code, was to build a program that could make and display a magic square of any odd size. That reignited that passion for magic squares, and it actually added a new aspect to it. Because so far, I'd always been doing this manually. But maybe I could automate it. I couldn't incorporate the entire method in that assignment, because I wasn't actually sure if it would even be possible to automate the even sizes, let alone how. And figuring it out would have taken a lot more time than I could possibly justify spending on that assignment. But eventually, I was able to build a website that could generate a magic square of any size and any sum, with just a click of a button. Hello there, I'm Simon, welcome to my channel, and welcome to the third and final episode of Magic Squares and Me, the series where I tell you pretty much everything I know about magic squares. If you haven't seen the rest of the series, there's a link to the playlist right here. In the previous episode, I taught you how to make a magic square of any size and with any sum. In this final episode, I want to take you through all the code I wrote to automate that process. As usual, in the description box below you can find a link to the magic square generator and the link to download the entire manual, containing everything I just said. Anyway, let's dive into the code. I'm not going to say too much about the front end of the website, because that's really just making the connection between the user and the generator. All it is a central function which waits until the button is clicked and then gets to work asking the user for input. It plugs that input into the main function, which uses it to create a magic square by the specifications. It returns that magic square to this central function, which then sends it to another function which displays it in a neat little HTML table. The manual actually goes more in detail, despite also claiming it won't go too deep. So if you're interested, go read it. One thing I want to point out is that before it asks for a sum, it actually calculates what the predicted sum would be. This is a thing I didn't go into in episode 2 because that video was pretty long already, and it doesn't really matter anyway. But it is in the manual, because you can use it as a guideline to know how big the sum could actually be. I included it because that's not really a thing us humans can usually guess intuitively, and if it's too far from the predicted sum, the numbers we're working with could get rather big, and we might go way into the negatives, which is fine, but not necessarily aesthetically pleasing. So that's why the program just calculates that and sends it along with the prompt as a guideline. So basically, the front end takes care of everything that has to do with collecting the input and sending it to the actual generator, and then displaying the magic square in the web page. So let's talk about the actual generator. The interesting thing is that the generator actually uses essentially the same technique a human would use, but it approaches it in a completely different way. The first thing a human would do is calculate the first number, because you can't start making a square until you have that. The generator is actually going to construct the basic square first, and then add the first number to all of the values, because that's the thing computers can do, and it comes down to the same thing in the end. The second thing a human would do is determine which category the square belongs to, and then use a different method depending on the category. Now, it would be totally possible to write an if-else filter, which tells it to do something completely different depending on the size. In fact, it still does something like that a little later. But doing it directly, like a human, would actually make it very complicated and could potentially break the code. That's because with the doubly even numbers, it would nest the small picture in a big picture of 4. The whole picture principle thing is easy enough to do without breaking, but the small picture could theoretically be any size at all, meaning it would have to make a magic square for that. And to do so, it would have to rerun the same central generator. I'm not entirely sure that's actually possible, but I think it is. But in doing so, it would have to reuse variables and overwrite them, which would break the code. At that point, I realized that even if it's possible to write that code in such a way that every eventuality is covered and without breaking it, it would get hideously complicated, and there had to be a simpler way to do it. And there is. The thing is that any magic square may or may not be a multiple of 4, meaning it may or may not need a certain small picture nested in a 4x4 big picture, potentially more than once. That small picture may be a singly even number or an odd number. At that point, it can't be a doubly even number. So that small picture may or may not need to be a Siamese magic square, maybe combined with a radar. That makes it possible to actually combine the different methods into one, and depending on the size, you can decide which steps to take and which ones to skip and which ones to do more than once if necessary. So the first thing the generator is gonna do is gather that data by running the size variable through some steps. First, it's gonna divide it by 4 until it can't anymore and count how many times it was divided by 4. That's a variable called the 4 count. Whatever is left after that will be checked by dividing it by 2. If the remainder of that is 0, that means it's even. So it's gonna save that fact in a Boolean variable. Then it's gonna actually divide that even remainder by 2, and that will definitely be odd. So that will be the third variable. Based on those 3 variables, it can actually get to work making the magic square and decide what to do and what to skip. Using that odd number, it will then make a Siamese magic square. That remainder might be 1, so that step could be a little pointless, but it'll do it anyway. You'll notice that that Siamese square is called the big picture, and the reason for that is that it's assuming that this will be the big picture in a singly even magic square. It may not be, but then it's just gonna skip that step. The Siamese square maker will set a counter to keep track of things and the starting coordinates. Then it will iterate over the grid, and each time it will set a couple of things to make sure it adjusts the coordinates appropriately if the coordinates push it out of the grid, or if there's something other than the placeholder, aka a number in there. Once it has the correct coordinates, it puts the correct number, which is actually the round number of the iteration. Then it adjusts the coordinates for the next round. Rinse and repeat until complete, and that gives us the Siamese magic square with a starting number of 0. There's 2 more things it has to make before it can start making decisions. The first is an array for the small picture, which it will need for the picture principle. But what that small picture will be will depend on those 3 variables, so for the moment it's just there. The other thing is a basic 4x4 magic square, which will serve as the big picture for the doubly even numbers. It might be possible to code the steps to construct that, but it's just a lot easier, since it's not going to change or anything, to just hardcode it. With all that set up, the generator now needs to check those 3 variables to see what to actually do. That's why there's a conditional filter here, aka an if-else filter. If the remainder was even, what's left when it divided that by 2 is 1, and the amount of times it divided the size by 4 is 0, that means the size they asked for is 2. So because that's an impossible magic square to make, there's no point in continuing the function any further. So it will now display a special paragraph in the HTML page and make a 2x2 array with half of the sum as the placeholder. And it returns that to the front end, exiting the generator. If the remainder was even and what's left after dividing it by 2 is 1, but the size was divided by 4 at least once, that means the size is 8, or 8 times some multiple of 4. So then it has to make an 8x8 magic square to be the small picture. So it subtracts 1 from the 4 count and then calls a separate function to make the radar. Then it will pass that radar and the big picture to another separate function which uses them to make a magic square. Now that's essentially what also happens when the remainder was even and when half of that remainder was more than 1, aka when it's a singly even number bigger than 2. Then it's going to also call that function to make a radar, except the size of the radar will not be 4, but whatever that final remainder was, aka the size of that Siamese magic square. And that Siamese magic square will be the big picture. And of course, if the remainder was not even, it doesn't have to bother with the radars at all. And it just prepares for the next step by redefining the Siamese square to the small picture. In the other cases, the small picture is just the magic square created with the radar. Anyway, the function that makes the radar will get the size of the radar as its parameter, and that size will either be 4 or an odd number. If it's 4, it's gonna make a boolean and iterate over the grid, flipping between true and false each time, except when the counter is a multiple of 4. And depending on that boolean, it'll set it to either n or z. That way it ends up with a checkerboard pattern. It definitely would have been easier to just hardcode this. If the size is not 4 though, it's also going to iterate over the grid, but it's going to run the coordinates through a conditional filter to determine which group it belongs to and which letter belongs there. Essentially, this is like a flowchart where it can just test the coordinates against a value and, depending on the result, do more tests until the code tells it to stop testing and write a letter there. Then it moves on and does it all over again. And in the end, it just puts the X, Z and E in place. And that results in the radar it needs. So at that point, the radar and the big picture are passed to the function that makes a magic square with them. Here's the thing. What's happening here is essentially the same as what happens when it just makes a magic square with a general big picture and small picture. That means those two functions can be merged into one, and there will just need to be something extra to find the number in the small picture using the radar. So the first thing it needs to do is verify whether or not the small picture it gets is a radar. It does that by looking at the first cell in it, though it could be any cell at all, and see if that's a number or a letter. So then it can just save that fact as a boolean and use it throughout the function. Knowing that, it's then gonna define a multiplier, which is basically the size of the small picture. If it's a radar, that multiplier should be 2, but the length of that parameter won't be 2, so it's just gonna check the boolean and define the multiplier accordingly. Then it's gonna make a grid to iterate over, and that grid will have to be the size of the total picture, so the big picture times the actual small picture, which is the multiplier variable. Then it's gonna iterate over that grid and do a little bit of math to turn the coordinates in the total picture into the corresponding coordinates in the small picture and in the big picture. The coordinate in the big picture is just the coordinates in the total picture divided by the size of the small picture, ignoring the remainder. And the coordinate in the small picture is just that remainder. So for example, if the coordinate is 7 in a grid of 8, the coordinate in the big picture is 3, and in the small picture it's 1. And the reason that gives the correct coordinates is because computers count from 0 rather than 1. So now that it knows what the corresponding coordinates are in the big picture and the small picture, it's going to define the modifier. The modifier represents whatever number it finds in the small picture, which will be added to an adjusted version of the number in the big picture to get the actual number that actually goes in that location in the total picture. So it's gonna test if it's a radar, and if it is, it will pass the letter in the corresponding location in the radar and the coordinates in the small picture into a separate function, which defines the small picture depending on the letter and returns the corresponding number to be the modifier. If it's not a radar, it's just the small picture itself. So it will just take the number in the corresponding location, and that will be the modifier. Finally, this function will calculate the number to actually put in that location by multiplying the value in the corresponding location in the big picture by the square of the multiplier. That's because the numbers in the big picture are not so much the values that go in the corresponding locations, but the order in which the small pictures are filled in with consecutive numbers. Each small picture has an amount of cells in it that is equal to its length squared. So the actual number the big picture gives us is the amount of cells times however many small pictures have already passed. And so the number that goes in the total picture is the number in the big picture times the square of the multiplier plus the modifier. So it will do that for every cell in the total picture and end up with a magic square the size of the total picture starting on 0. And that means it's time for the final step of the construction of the magic square, which is dealing with the 4 count. This part is super simple because there's already a bunch of functions to do the hard work. So it's going to define a copy of the small picture, which is the magic square created through all those steps. The reason it makes a copy is because making the next small picture is going to use the current small picture. So using the same variable could be problematic. So then it's going to iterate through the 4 count, each time making a new small picture using the previous one as the small picture, and the basic 4x4 square as the big picture. That depends on the 4 count though. So it's possible that it only does this once, or it might not even do it at all. But the point is that it can do it as many times as necessary. And at the end of that, it has the basic magic square of the requested size starting at 0. But that's not the magic square they asked for. That's just the foundation. So the final step is to add the first number. So it's just going to make that a variable, defining it simply as the entire formula. Computers can just do that. And then it's going to iterate over a new grid of the requested size and define each cell as the number in that location in the basic magic square plus the first number. And at the end of that, the generator finally has a magic square of the requested size with the requested sum, which it returns to the front end. It's time to wrap up this video, and with that, the series. I do hope you enjoyed it. I'm not planning to make any more videos about magic squares, so this should be the finale. I'll still be making videos though, so if you enjoyed this series, please check out my channel for more. In the meantime, everything else you can do to help the channel is in the end screen as usual. I'll see you next time. For now, thanks for watching.